So a real-time system is a system which must satisfy explicit response time. So, let me give an example of this. When I say response time, it is the stimuli. For example, if I ask you a query and ask you to answer, but if I give a time frame or a deadline attached with it, then now it becomes a real time. So, but you may reply in your own time. So that's why the response from you when it comes, it has two meaning. One is implicit response time, implicit in the sense in your own way, and explicit in the sense I am defining a particular time for you guys. Okay, so a real-time system is a system which must satisfy an explicit response time. For example, if I ask you guys that the capital of Brazil, and I give you 1 sec, and the time is up, is an example. You might be knowing the answer. So the capital of Brazil is what? Rio de Janeiro. So, but the amount of time you took to respond in your own way is an example of a implicit response time. I want in a second, but you will reply in 10 seconds, 20 seconds, maybe tomorrow. You're not in a hurry from the system perspective. But an application is very, very, explicit about knowing this information. If I don't know this information, then I'm going ahead, So I feel like, okay, this system doesn't work for me. It's a stupid system for me, right? So something like that. As an analogy, you can think of. So here's what I have charted on here: a real-time system that must satisfy explicit response time constraints, or also risk severe consequences, including failure. So you should be also aware that when with this failures arrive, and it must be, environmental control. So you can see here I have placed a time which is freezed or frozen inside. And the idea of this is something unique. So what does it mean is that irrespective of the extreme condition of environment, the time piece will work exactly as it used to work in a normal condition. So time cannot say that, hey, I'm feeling cold, so 20 seconds is equal to 1 minute. And if I keep this into an extreme temperature of 500 degrees centigrade, which is beyond this melting point, or 100 degrees centigrade or 60 degrees centigrade, it will start saying that, hey, now 300 seconds is equal to 1 minute, or vice versa. I think I said the opposite analogy, that if it is cold, it will go slow, so it will take something like 100 and 300 seconds to become 1 minute. And so very hard, then it starts jumping around, says 20 seconds equal to a minute. So it cannot do that. It has to be resistant to this kind of environments, and that's real-time system. And this including this failure aspects which we have written. This failure is the point of category, guys. So based on failures, there are 3 types of real-time system. One is referred as hard real-time system. The another one is referred as a soft real-time system, and another one is a firm real-time system. Now, hard real-time systems are the ones which are very critical applications where we develop, and soft reals are like most of them like to develop them because consequences of failures are connected with this. And soft, as there is less of consequences. And a firm real-time system is an answer to not being very lousy like soft real-time system. It must try to meet similar to an hard real-time system. So there is a bondness and responsibility which is more severely attached. Okay, so let's try to see in hard real-time system. If you look at a hard real-time system, here, failure to respond to one single event is referred as complete system failure. Okay, so a system which fails to respond to one single event is referred as the complete system failure, entire system gets crashed down. And when I say complete, is not superfluous. It is a matter of life and death in case of these kind of development. And hence there's a huge amount of time spent in integration and testing. Sometimes the lifetime of these project developments are like 30 years, 35 years, 20 years. And slowly, if it gets mastered, it can, start reducing its development life cycle. But usually these kind of critical applications are very hard to develop, like Lockheed Martin or RTOS or Airbus. There are a huge amount of JAXA, NASA, ISRO. I mean, very good names where they really make some very strong, hard system, and if it fails, it really goes off the line. Let's look at some examples. This is a very nice video. It's a docket which is getting detached from a space center on top, and then it has a lot of soil samples which is being bought. It is trying to geoposition itself. That box which is here is running a VxWorks running on a PowerPC architecture. It's trying to have a paragliding on after this, and it's trying to reposition himself and land it accurately to a place where scientists could run and capture and see the soil samples there and get the people I would say going on that how things would work out. You can also see this is an example of a threat launch from some of the country. And here you can see it's in a Ashkelon. Ashkelon is in Israel. And you know that Israel is very popular for getting a lot of bombings, disturbance, and so on. And it's trying to show you that, how GIS data, which is geographical data, and are being simulated by using this, software. And it's trying to create a mechanism via which you can see on the left-hand side a graph. This is a Linux-based graph being driven on top. And see, you have the green colors which you see, they try to see the approximation in the system. And the sensor modeling starts creating probabilities for them with the distance and the speed at which they are coming. You can see that missiles are being launched from there, and now it's trying to intercept, and it will catch them and blast them up. So you can see they're trying to negate these kind of threat launches. So this is again the launch. And now again it will say, so AGI is a software simulation tool. So if you are in Airbus and other things, or if you are in aerospace defense based product, and you can see how the blue lines are coming, and from here we have applied the retaliation tests, and they are really deflecting them and thrashing them off. So this is something which is a very good example of how things can work. Anyways, of course, a way to tell you that how hard it is to develop the hard real-time system. Similarly, you can see here the 4 billion development effort on Boeing 777. Okay. And 50% of the money is spent in integration and testing. And usually the lifetime is like 15 years and all. Some of my colleagues and all, I remember ex-colleagues, they were working in Hamilton CL for like 10 years there in Hamilton, for aerospace and defense areas. So only integration and testing. Now you can see here, it's a French Guiana, 1996, 4th of June. 800 million software failure it is. One variable was not initialized inside a while, and then it went crashed because of this. You can see launching on the left-hand side, a boom on the right-hand side. There you go. One of the most exaggerated problem, you can see Independence Day, America, July 4, having a very embarrassing situation in 1997. And his Mars lost the contract because of real-time priority bug. And they tried to, and VxWorks tried to fix this. And somehow, they became billionaire over a million. So they were hard real-time. Soft real-time systems do not need much example because everything you see around you is mainly evolved around soft real-time systems. So you can see the consequences during these kind of system failures are not very agile. So it's not like the matter of life and death. And if you respond to fail to one single event, it's not a complete failure. It's like it will degrade the performance beyond what was considered to be good or expected. Timeliness is good to have kind of a thing, but you don't need to provide a guarantee that it has to work within that. A little bit of up and down is fine. So calibration, testing, these all things can be reduced to cycle. Product development is faster in these cases, and overall less risk in this kind of development. And you'll find a measure of the players in these because it's a risk-free environment. Not many players are in the world who would like to take themselves up and do some really hard-hitting jobs like hard real-time system. Now, firm real-time system is an example of in between. Here, timeliness is important, but there is a threshold kind of a thing. So you can perform certain kind of a delay, but beyond a certain delay, its threshold is like going to be. It's unexpected. You shouldn't be doing it, and that can cause catastrophe. So your systems usually will get dashed. So if you look at practical systems around which we are usage-based or use-based systems, they are often soft real-time system, and need not to break your head much on form and minute differences between them. But you should know these are some categories which are coming up. The question goes to you all. So assume that I am a real-time application, and you guys are a real-time system. And if your average response time is 20 seconds, 2 seconds, and 0.2 seconds, how suitable are you for me? What do you guys think? Let's pause for a while. Think and tell. Nobody? So let me answer you this quick. So if I choose you and you respond to me in 20 seconds, then you're very slow than what I'm expecting. My response time is 2 seconds, but you're responding it to me in 20 seconds. So naturally, this is not a fit for me. So you'll become a software diamond system. Now, when you give 2 seconds, it's an exact fit for me. I love this system because you are meeting my expectation within the boundary you're giving. However, the problem is that for me, you are fine. But what if I have an application which is less than 2 seconds? So, there cannot be one single answer that you will be suitable. But it's like, obvious choice that 0.2 seconds, why do I choose is because, you're very, very fast. So on an average, you're responding to very fast. So every 0.2 sec is what you come and see someone is looking for a service. Rather than in another case, 2 seconds, another case, 20 seconds, every 20-second lag. So I have an 18-second lag, I have a 0 delta lag, and I have no lag in 2 seconds because you're responding much, much faster than anyone else. Just like, you think analogy-wise that if you have to buy today some kind of a gadget, then, you want to actually buy by considering certain facts like, hey, at least for 5 years it should come to me, or 3 years it should come to me. If I'm buying some laptop or something, why should I compromise? Let's buy, even though I may not utilize the entire feature of them, entire power of the processor, entire features of those laptops, I will still like to take that because for the next 5 years it will come, So in this consideration, 0.2 seconds can also be fit. So 2 is a good answer, but 0.2 is good that even though you have tomorrow an application whose response time is less than 2 seconds, you're a part of it, correct? So that's a good choice in overall. Okay, now let's go to more important thing called as real-time operating system. Now you see, operating system is a very notional term from system software perspective, because it is like what is shipped from the client, So for some people, operating system can be that it is having everything, It has the bootloader also, it has the kernel also, it has a root file system as well. And for some, it may just refer to a kernel and so on and so on. So OS is usually customized for certain hardwares, right? The system software, which drives the entire hardware and acts like an interface. And it has a collection of lot of application and softwares both together. But in certain distribution, typically in open source environment like Linux, it is very hard to say what do you mean by an OS, because it's the vendor which ships and they control, and that's true for others also. Even in Windows, when you say Windows operating system, the notion of an OS is not only the bootloader, the kernel, but also a lot of Explorer with applications like Notepad. That will be available with us. MS Paint, or of course MS Paint is dead now, but some other browsers like eAge or Internet Explorers are expected to be there. So I don't need to pay to install those apps. Unlike if you want to use something like Microsoft Office, so then you need to pay for it. Or if you have something else, you need to perform these kind of things. So that's what is operating system. And real-time operating system really wants to extend the real-time behavior, what we just studied now. So a kernel or an operating system. So let's try to define them, guys. So real-time operating system is a system which tries to satisfy the worst case response time of an application. Now there are three things you should know about: average case response time, best case response time, and worst case response time. So if an OS can be designed to answer the worst case response time of an application, they are truly a real-time OS. A lot of OSs are available. And what they provide is, they provide a lot of features. They provide multitasking capability with an application. They provide ability to define priorities for task. They allow you to have driven with those applications which are through some certain unique priorities, or you can have some deadline-based oriented scheduling. Of course, they may not provide you, but you may have provisions to learn and apply them. You see a behavior, you model your application permutation, task permutation and combination, and then you can change them. You can apply some deadline-oriented scheduling, and that can make your system very, very predictable. It also provides programmer-defined interrupts, so that you can program your software interrupts. Now there are a lot of unique features in for a real-time OS. The top 4 are the differentiators, and the bottom 3 are something which is commonly available in every OS. So an ability of deterministic behavior, low interrupt latency, low memory management, scalability are the primary differentiators. That's how it makes a normal OS also an RTOS. And multitasking, multi-threading ability, multiple task priorities, support for preemptive scheduling is a part of most of the modern operating systems. So it's very common stuff. You must know them. For any OS, it will be applicable. But when you talk about real-time OSs, the first 4 really stands out. Okay. Now we have to understand among all of them deterministic behavior first. So I think you all guys know what do you mean by deterministic behavior. A deterministic behavior you can think of is a predictability of the system. Okay. So can you determine the runtime aspects of an application which is run? And you saw that we started our sessions with finite state machine, which is a primary way of finding whether your system is deterministic or not. And if it is non-deterministic, we have to convert the deterministic aspects of those non-deterministic in certain environment. So it allows you a good predictability. Now, The second is the low interrupt latency. So it's not about only interrupt latency being factored, but low. How fast can you respond to the external world? The third talks about low memory requirement. Can you write your application or task which can be constrained within certain bytes or KBs or MBs? If you have gigs of memory you want to consume within megs, if you have megs of memory you want to consume in terms of KBs, if you have KBs you want to convert in terms of bytes, and that kind of requirement is needed. And scalability is like, in real-time OS, you don't need to have every feature. And a lot of devices may be there which may not require the entire network, all the file systems, all the interoperability of the systems, and so on. So, scalability, it means can you scale it up or scale it down? Scale is like measurable. You can add some components, you can remove some components and features as and when required as a part of your kernel configuration. At the end of these courses, what we'll be learning is the same thing. We'll talk about them. I had the embedded Linux session where you learn about how do you configure a kernel, build a kernel, compile the kernel, test the kernel, and all. But we'll do it in a stage wise. So as of now, we see that at the mid of December you will be almost through with this course, going in this particular pace and schedule what I have derived. But let's see how it goes. I'll be trying to be flexible. So just trying to just show you a minute of deviation. So I think today we are here, 27th of October. You guys can see the screen, right? So as a part of Foundation, we are here today, and we'll be moving ahead. And then we'll have essential C for embedded, and then C++ for modern developers, then embedded Linux using QEMU. So here is where you learn about all those booting and kernel programming, testing new kernel images, kernel compilation, and so on. So just to get you the context, we were talking about this, scalability. Now, multitasking is an ability via which, on a single CPU, you can have more than one application juggling and trying to give you a much better experience. You could also use multi-threading if you have more than one course. Provision for a task which can have multiple priorities. So a task can have a low priority, and dynamically, if required, it can change its priority, and so on to meet certain deadlines or allow other task, which is the most important, to take over the CPU and do some job, and so on. And of course, preemptive scheduling. We'll learn about preemptive scheduling in a later course. Okay. Preemptive is an ability, in short, to monopolize the CPU based on certain priority using criteria. Though, the difference between real-time OS and a general purpose OS is getting blurred, it's important to, place them here. So like, real-time OSs usually do not support any virtual memory. Conventional OS does that. Now, what do you mean by virtual memory? Do you guys know what do you mean by virtual memory? Anybody? Let me see a chat window. No. So, virtual memory is a software technique. It's a very classic software technique by which we manage constrained RAM area. So if your physical memory is lower than what a CPU could really address or your application demands, then the operating system uses a software technique using virtual memory, via which it tries to, give notion to the application that I have all the memory with me, guys. And internally, they manage with a given set of physical memory. So they use different techniques like overlays, paging, or swapping kind of partitions by which they try to achieve this swapping in, swapping out, paging in, paging out, or overlays, loading in stages certain portion of the program in certain orders to achieve these kind of thing in OS. So it's very messy. And RTOSs may spend too much time and in these kind of ordering and logic, and it may lose a lot of time. Again, it's very hard to say that virtual memory is not supported in RTOSs. Modern real-time OSs have got already a lot of virtual memory. Typically, let's say if you look at an ARM architecture, you have something like M series, then it doesn't have any MMU, hence there's no virtual memory. But if you have an MMU like A series, so Cortex A15, A11 in the past, and then A37, 85, A75, A76 series, all of them are very good example of that it has inbuilt MMU. And naturally, in these cases, they will be using this. Application program is single purpose, there's general purpose. Scheduling policy is on priority here. There you have round robin fairness. So you have a time slice given there. Even IO processing usually is performed by application programmer. They directly talk IO to the pin ports and all. Here we use drivers to do that. And the same thing, as I said, a very simple RTOS we are talking on the left-hand side, guys. If you start thinking of modern operating system and real-time OSs, you'll find all the things on the right is available on the left-hand side with some things. So you can be and or kind of thing. So it's a blur, but be aware some people are very specific. When they're specific, they are talking about 8-bit, 16-bit controller driving an OS. Then left-hand side will apply. An example of some of the commercial real-time OSs like VxWorks, Monta Vista Linux, TimeSys, RedSonic, QNX, SMX, AMX, C Executive, OnTime, ThreadX, or Nucleus, I should have said, RT Linux. You have MicroItron. RT Linux is now referred as Wind River Linux. MicroItron, UCAS 2 and 3 now from did I mention PSOS, by the way? Hey, PSOS was a classic. Anyway, it's been killed by VxWorks, so you can think like that. iOS, Symbian, WinC, Android, mobile-based operating system. All of them are commercially available real-time operating systems. Now let's take a small preemptive study about these commercial OSs, what they do contain. They have a lot of components. I've taken VxWorks as an example. So, first and foremost, you'll see there is something called as Board Support Package, or BSP. Now, BSP is like a package, means it's a software, and it's to support the board to start up and do some basic activity. Analogous to a BIOS is what you can think from programming perspective, So if you have a BIOS for a PC, you can think of a BSP for a embedded board or target boards, okay? And then BSP has some debug agent by which you can perform debugging. If you remember, we spoke about debug agent yesterday. By using JTAG, right? Or BDM or Nexus, one can perform some very basic, probing of the system and draw some diagnostic and see if there is some hardware fault, and then try to modify the BSP and then do the same configuration, see again and again till things are right. Now, bootloaders will drive on top. You can see the core kernel. The VxWorks has a microkernel. It's a smaller size. Size is one of the things to be smaller. And then the way they operate the services. Then you have the entire core OS, and also has runtime like POSIX library. I think I was just pausing for a minute to really wondering. Do you know what is POSIX, by the way? Anyone? It's a standard. So POSIX stands for Portable O as in operating, S as in system, I as an interface, X as in Unix. So portable operating system for Unix-like interfaces. It's like a draft. You will have a set of API which every Unix-like machine will like to follow for providing backward compatibility or portability. And it's a very strong standards. A lot of products have been built around POSIX API. And then, of course, ANSI being one of the oldest and classics of all time. And market also demands a lot of scalability, third-party OEM models to be integrated. Do you know what is OEM? Anyone? What is OEM? Stands for Original Equipment Manufacturer. For example, Samsung is an OEM. It brings up its own equipment, okay, as part of its manufacturing. Even other silicons could be a very good example to draw on this. All right. So with this, features, let's move to understand what do you mean by multitasking. So, a lot of people think multitasking is a parallel computation, and that's wrong. The term multitasking is used for sharing the CPU, one single CPU, across several other tasks or multiple tasks, threads, or processes. Okay. So that's something multitasking. Now let's look at, in the real-time OS, the most important thing inside is the kernel. And the kernel is a system software that manages the time of a microprocessor or controller, typically the ticks. And it ensures that the most important code or the program should run first. Allows multitasking. And it does a lot of things at the same time. It gives a notion, really. It doesn't do that, but it gives you a feeling that, hey, all things are running together. And application is broken into different tasks, so it's easy to maintain our application. And it's like, you're giving a feeling that you have more than one CPU involved. So either by time slicing or by some priority and time slicing combination or some predictable sequencing, we can have a multitasking achieved in kernel, and provides very valuable services to your applications, like can give you synchronization management using semaphore, event tasks. You can also use timer delays. You can use interprocess and task communication with synchronizations for race conditions, right? Now, how many types of kernels are there? So kernel are two types. One is called as non-preemptive kernel, and the one is preemptive kernel. Guys, this is often asked by most of the people, that can you differentiate between so, provide valuable services to your time. That's something which you should be knowing. Right? Let's look at non-preemptive kernel. So, non-preemptive kernel is a kernel which is, one of the simplest real-time kernel. A lot of people start arguing, thinking non-preemptive kernel is not a kernel, a real-time kernel. But that's not true. Very simple kernels, okay, in the past, if you look at 70s, 80s, and 90s, there has been a loads of code written which are simple kernels driving, smaller devices like 8-bit, 16-bit devices. And they're non-preemptive in nature. It means, it is not the kernel which gets involved in sequencing and executing the task. So kernel does not decide the way a task is going to run, which task will run first or second. And it's the application which will drive this, guys. If I have an application running, and if I have 2 or 3 tasks to do that, and if I have first task starting, then followed by that second and third, then it's going to be sequenced. It will start from task 1 till it completes, go to the task next, and then it will go to another task. So it's a sequential execution and driven by the application guy. And suppose if that combination didn't work out, then you have to go back to your source code, edit this combination, and then again start. Even that doesn't work out, keep doing that. Or split your task appearances for again and again. So it's a very fairly simple, design, like you can think of some remote controllers or some kind of a small 8-bit toy kind of a projects. They can be very happily running on a non-preemptive kernel, right? So yeah, but of course interrupt is enabled, because without interrupt, how do you take the external world events? So interrupt is always enabled, whether you have a preemptive kernel or whether you have a non-preemptive kernel, Okay. So what advantage do you have that you the completion time? Okay, who's that? Ajit, why don't you mute yourself, man? Thanks. So what are the advantages? I said you can predict the completion time for an application. And the second thing, which is very unique, is that there is no dynamic interference of the data. So if you have a global variable, you don't need to really guard them, because unless until one of the function completes, another function cannot run, So by default, C and C++, classic C and C++ are an example of a non-preemptive supportive kernel. So it's like, it will run only in sequence. So if I have a function 1, function 2, function 3, before function 1 is over, function 2 doesn't run, something like that. So there is no need for you to worry about the global data. The third very important point, which I haven't mentioned over here, is that there is memory constraints advantages also. That in a non-preemptive kernel, all the tasks can share one single stack. So I can have only merely 2 stacks to manage the entire system. One stack for interrupt handling and another stack for the task. Whichever task comes, the same stack can be reused. Reason is, we don't need to store the context of the task, because the task till it's complete, no other task will get the job, correct? Or will not get the CPU, I would say. Yeah, but interrupts can arrive. So naturally for interrupt, I need to have always a separate stack. Remember, irrespective of the type of kernel, the interrupt must be serviced as quick as feasible. And hence for them, you must have a dedicated stack to, perform this work. Yeah, of course, some disadvantages comes in. The complex systems cannot be very, very easily predictable. You cannot have runtime relinquish controls. You cannot achieve like real-time capability in the systems, and so on, guys. So that's a catch here, that you may not be able to actually take advantage of. As you can see diagrammatically, a low task is trying to run, interrupt arrives, and ISR will try to make a high task ready. Even though ISR tries to make the higher priority task ready, it is not running. It's still the low priority task on the top running. After the first task is over, then is where the high priority task runs. So the meaning of high priority does not exist in this non-preemptive kernel. That's what it is trying to portray. Now we'll talk about the preemptive kernel. So preemptive kernel, naturally, this is a most required kernel in the real-time systems. So nowadays, most of the kernel provide this as a default feature in the system. Whether you use a QNX or VxWorks, or you have a PIC-RUM OS or Microtron or FreeRTOS, whatever, all of them have a preemptive kernel. So in preemptive kernel, what happens, that every task is given some default priority, guys. So there is a priority, which is usually a number, and of course the user provides it, and kernel also provides some default number for the tasks. So what happens is, based on the priority, it is the kernel which will decide which is the next task which is going to run. So the importance of the kernel in relinquishing the next task becomes very vital. It means in a preemptive kernel, the execution of the task is determined by the kernel. In the non-preemptive, it is done by the application. So we will decide that. Of course, here we have to change the priority. We have to decide the priority. Still, kernel will dynamically decide based on the priority, but priority has to begin by us based on condition and use cases. It's a little bit harder to imagine about the consequences and use cases which will arrive at runtime for predictability. So prediction is a little bit tough. But advantage is, it's a real-time completion. If we know about the higher priority task, I know that these are very important tasks can be first taken care, then let the second medium priority task, and then don't care task. Our life is also just like this. It's all a challenge of scheduling, right? We always try to do the most important task first, and of course we will have a criteria for how to define which is the most important. Right now, getting $2 a day is very important, or getting to the class is very important, or doing assignment is very important, or filling the petrol right now is very important. So depending on no, the preconditions or criteria, you decide priority, correct? And you once you've done that priority, then the second, then the third, and then no. So in that case, you're sure about high priority being predicted. A disadvantage is that it will have conflict data between the global variables. So if you have a low priority task running using a global variable, and if it is interrupted by an ISR and then a high priority task comes, it becomes a mess. So data race is a very, very high consideration. Second disadvantage, which is not mentioned over here, you should remember is, or make notes. I hope that whatever I'm talking, you guys are also having a pen, paper, pencil, everything with you, and you're trying to make certain very important notes. It helps you to remember in the context. I always used to do this. I still do this. If I am attending some webinar or WebEx session which is of my interest, I usually pen down some of the very important aspects and then do Googling and extend those informations and then create some concrete knowledge base around me. I can also suggest the similar things to you. Anyway, so one of the disadvantages which I didn't say is again from the memory perspective. Because the tasks are preemptive, they can switch from one task to another at any point of time because you don't know when interrupts arrive, when the event will take place. Hence, it is required to have dedicated task-based stack, or each task will have its own stack. And because of this, the memory requirement in the program becomes very, very high. So naturally, when the application is very, very simple, I will go for non-preemptive. When applications are going very, very complex, then I also need a better power, better CPU, better this memory, and hence, this is one downfall that you're simply increasing the budget in your application by including a preemptive kernel. A lot of people have to say, but it's not really so because you need your richness in the application. You need the behavior of the applications to drive this complexity. So naturally, this is an overhead that you need multiple stacks. Each one stack. So if you have to have 30 stacks, so a base task means dedicated 30 stacks are required for you. An example of a preemptive kernel doing a right job, low task being interrupted, and then it tries to make high priority task run, high priority task runs, and then after this, lower can start. Okay. So now we are reaching to something back to square one. Guys, I'd like to take a minute's pause and then resume the session. I'll just take a small break. Let me get a glass of water and join you guys. I'll mute. Yeah, guys. So let's roll back to the same thing. Now, see, the idea was to go through and explain you about the types of the kernel before I get into a very important concept called as low interrupt latency. Okay. So, that's the reason, I explain about this here. And the same slide reappears after going through this. So let's understand the most important foreground processing. Interrupt handling is also referred as foreground processing. And task handling is referred as background processing. And we can understand about interrupt latency, responses, recovery, deferred interrupts, ISR processing time, and also a little bit on non-maskable interrupt. This is a very good example and a diagrammatic representation of that, how the entire interrupt related context works. As you can see, there's a yellow stripe which represents to a name as task. On the bottom line, we are talking about there is something called as a pink line, which is having task B. Now, an IRQ is an example of interrupt request. Usually it's a line, it's a bus attached to some kind of device, logically. A device initiates an interrupt, an event gets triggered on this line and is passed on to. Now, while this IRQ starts, a task in the background keeps running. So if nothing, at least an idle task runs, So a task is running, and when the event arrives, what is the amount of time it took to start servicing the interrupt? Okay, which is the example of an interrupt response. So first we'll talk about interrupt latency, then interrupt response, then interrupt recovery, then task latency. Okay, for very important terms for every embedded developer, typically for software based, metrics to be derived. So when you have to calculate some kind of worst case response time, interrupt becomes a very important criteria for measurement. Okay. So you can see interrupt latency is nothing but the time since when the interrupt has arrived, plus the time under which the task has disabled the interrupt, or it could be that, while the task is running on that line, it has disabled the interrupt. So that becomes a latency. It's increasing. It adds to your latency. However, how do you know the response time? So there is an example of response time. So in a real-time kernel, the response time is nothing but interrupt latency plus the amount of time consumed by the kernel to save the CPU context, in purple highlighted here. Okay. And this one. Then you can think of something more, before it starts giving you the service, kernel has to do some additional job, which is called as the time taken by kernel ISR entry function. It means you may be like, sometimes a CPU context may not be sufficient to store the entire information of a task. So in those contexts, kernel has to do some additional job, like, some memory pages which are locked has to be stored, or certain pages which has to be, unflashed, or certain information has to be stored somewhere in the backup storage or some storage, or it has to be referenced from someplace. Some lines has to be disabled or enabled. So kernel specific stuff has to be performed. And then is where you have the user program running. Okay. This is your response time. So interrupt response is the one which describes the response time of an application. So we can formulate it if you want to take down that interrupt response is equal to interrupt latency plus the CPU time context saved plus kernel ISR entry function time. Now user ISR code is the response, end response, execution time. So it's like ISR processing time. So if somebody is saying in general ISR processing, it is referring to the user specific ISR, Now we will talk about interrupt recovery. Now interrupt recovery has two definitions, guys. Okay. One of them, when you are having a non-preemptive kernel, it's a bit different. And while you have a non-preemptive to a preemptive kernel. So while you have a non-preemptive kernel, the interrupt recovery is referred as the amount of time kernel takes to perform the exit activity from the kernel ISR, and then the amount of time it takes to restore the previous context of the task, CPU context of the task. Now this is true for non-preemptive, because in non-preemptive, the task, I will go back here to say that if you have a task running, this is non-preemptive kernel, right? So as you can see, a low priority task is running over here. Interrupt has arrived. Interrupt has made a new task ready, but it is not running. Actually, this task is here, but here it is not going to run. Why? Because it's a non-preemptive kernel. After the ISR gets over, ISR will be accepted. It will still be the older task which will run till completion. Once it is done is where it will relinquish the control for the next task. So naturally, in this case, kernel will bring back the same task back to the system, which is what we are trying to, show over here. That is over here. This is kernel exit function, and this one is your actual time to restore, which is the old task. So from here, you can see a green direction saying task A will again start, which is the time taken from return from interrupt added. Now, if it is a preemptive kernel, then the job is a little bit different. In preemptive system, naturally you will perform the exit, kernel will perform the exit related activities, like bringing back those or clearing certain memory or bringing, certain information which it could not be storing. It could not be storing as a CPU context, but it required extra memory for doing that, and so on. Of course, the CPU context now restored can be done, but it has a search penalty. So it has to find which is the next so there is a search penalty, lookup penalty, which gets added, that which is the next higher priority task which is ready to run. And by restoring that return from interrupt, the new task starts running here. Task B has a higher priority task. So this HPT in this case will be the one which will be running, guys. So that's the complete aspects of the interrupt recovery. Now, if you look at a task latency, sometimes they may ask you what do you mean by task latency. So task latency, you can say that it is equal to interrupt response, okay, is equal to interrupt response plus the user ISR, the time taken for you to execute the user ISR, plus interrupt recovery. So interrupt response plus user ISR code plus interrupt recovery is equal to a task latency. In simplest word, a task which was running, once it got interrupted, till the time it resumes its activity is referred as task latency. So calculating a task latency in a non-preemptive kernel is easy, but it's a little bit tricky in preemptive kernel, right? Because if a lower priority task can be intimidated by a higher priority task and it has to be silent, and high priority task will come and will keep running on the system. Don't you think so? Correct? So that can cause something. I think, guys, today I will not like to overpour. Let's keep up to only this aspects. We learn about the real-time systems first. We learned about hard real-time, soft real-time, and the firm real-time systems. We spoke about some examples, certain videos about critical systems. Then we spoke a little bit about what is a real-time OS. We took an example of the characteristics of OS, comparison between the features of the real-time OSs. We also spoke a little bit about the two core features, some of the 4 core features and some of the very common features. We tried to differentiate between the attributes of RTOS and conventional OS. We spoke about certain set of commercial real-time OSs which are very popular. Not all, but some of the handful list. We spoke about the different components it can provide. We naturally didn't spoke in length on these components that an application can be triggered by a web server. It can have Java environment. So these are some set of packages, guys, to do some job. But mainly it was more about the kernel aspects which is required furthering. We learned about those standards it supports, scalable. Equipment manufacturer modules are supported by them. Then what multitasking refers to, the importance of the kernel to drive a microcontroller's or a processor's timer, and the most important task being executed. Types of the kernel like non-preemptive and preemptive kernel, the advantages and disadvantages of them. We also understood about interrupt latency, so interrupt related activities. So handling of interrupt in real time needs to know the knowledge about latency, response, recovery, deferred, and ISR. So I didn't spoke about deferred services. I can tell you what it is right now. So the entire interrupt, services are split into 2 parts. If an ISR is there, you can think, or interrupt is there, it is 2. One of them is called as the top halves, and the another one is called as bottom halves. Okay, so the top half are the ones which talks about such interrupts which must be immediately, acknowledged and served immediately. Acknowledge and immediately serve. The bottom half interrupts are the ones which must be acknowledged immediately, but can be serviced at a later point of time. Like open source Linux operating system provides a lot of bottom half handling by providing you some kind of tasklets or work queues, or even bottom halves in your classic old kernels. So they register a certain set of services which can be done at a later point of time. For example, anything for packet movement through a network on a net IRQ on a NIC or a network interface card can be performed later, versus if you have a keyboard which is a native interrupt. So the keyboard will be given more higher priority, timer will be given, onboard will be given more higher priority than the external components, something like that. You can start thinking, and some other PCI will be the next. So we can have this priority. Of course, we can configure, change them based on our desiredness, but that's how it is. So you can think, because of the bottom half, this deferred service routine comes in picture. So what could be a deferred one? The one which is not being acknowledged. So bottom half is an example of ISRs which will be running at a later point of time, and hence that's why it is referred to as deferred service routine. Okay.